Hi, good morning, guys. Let's wait a minute. It looks almost 10 a.m. Make sure everyone is here. Okay, so let's get started. First, I'm going to introduce. So first, I want to thank you for joining me this morning, and I want to introduce myself and my company. So I'm Zifan. I'm the application engineer of Singularity Engineering. We are a San Francisco Bay Area based company with a full portfolio of answers simulation tool, which includes structural mechanics, fluid dynamics, and low high frequency electromagnetics. So today we are going to present about how we can fast design our motors. So that's what the webinar name, Rapid Motor Design. So there's two tools we are going to use today. The first one is going to be ARM Expert, and then the second tool will be MAXWELL. So for people may or may not heard of MAXWELL, and some people may hear of ARM Expert. So I'm going to give a very brief introduction to these two tools. ARM Expert is a designer of electrical machine and generator can enhance Answers MAXWELL with ARM Answers Expert, and it's a template-based design tool. So together, MAXWELL and ARM Expert can create a truly customized machine design flow to meet market demand for high efficiency and low cost machine. So the reason why we are using ARM Expert is because using this tool, it can help us analyze motors and equivalent magnetic circuit model. ARM Expert can calculate the machine performance, make initial sizing decisions, and perform hundreds of what-if analysis in the matters of seconds. So next tool will be MAXWELL. So MAXWELL people usually use for all kind of low frequency magnetic simulation. So in the case of motor design, for example, for interior permanent magnet synchronous motors, MAXWELL is capable of doing efficiency map analysis, system level simulation, inductance analysis, eddy current of permanent magnets, and thermal demagnetization analysis, etc. So this is a very brief ARM Expert and MAXWELL introduction. If you are interested in more detail, I will post a link below after, and you can check it out. So next, we are going to jump into our tool, ARM Experts. So first, we will launch our electronic desktop. So this is the electronic desktop which I opened it already to save our time. And here is the environment of the electronic desktop. So let's first create an ARM Expert design. So here you can see there are many different type of motors. So for today's example, I'm going to do a three-phase synchronous machine, or three-phase synchronous machine. Yes. So let's go next. So once we have this, on your left-hand side, you can see there's a project manager. So here you can see we have the machine, stators and stator slot, winding, rotors, winding, shaft, etc. So for ARM Expert, you just have to follow step by step to complete all the setup and set up the analysis. Then it will run automatically. So let's do some setup first. So here is the machine type for ARM Expert. So we can see here, give you the machine type information. So for the number of poles we want to be 6. And let's say the friction loss is ideal, and we will have a reference bit is 1000 RMP. And on the right hand side, you can see there's a description of what each term means in case like some of term you may or may not know what it means. So let's actually give you a value for the frictional loss. So let's just apply. And if we go next, just double click on status. So we will give it, it's a, the stator is an outer stator. So let's, but if you are interested in doing a inner stator, you can do it as well. But in this case, we are going to do an outer stator. And here we will give it here is the outer diameters. And next, we have the inner diameters. We have the length of the motor. Next, we will have the stacking feather 0.9. We want to give it some steel material. So here, ANSYS have a very wide range of material database. So you can basically find a lot of very common material in here. If you cannot find the material you want, you can always add material. And you can define the properties of the materials here. So in this case, we are going to use M1924G steel. Okay. So another thing to mention is if you want to enter a BH curve, you can always do a BH curve for your personal material or customized material. Yes. So let's go next. And number of slots we will have 72, and here you are going to define your slot type. So we have 6 slot types as a default option in ARM Expert. If you want to define your own slot, no problem, you can do so. But in this case, we are going to use number 3. And we have also, you can also do the lamination setters, and I will go ahead and skip the skill width and this pressboard limits. So let's next apply. So you can see there's a outer the stator shape here. And next, if we go ahead and define our slots, so we don't want to do auto design, and you can see your property down here as well. So in this case, we are going to, so if you can also do a parallel tooth. That means if you look at here, that means BS1 is equal to BS2 if you do a parallel tooth. But in this case, I'm going to define all the settings since I have the data for this. So next, BS1. So if you don't know what are all these name means, you can always refer to the description, or there's a picture shown here. So let's go next. If we go winding, okay, and let's go to a winding layers. So we have 2 layers for the windings, and so for the winding type, we can do like a half coiled or full coiled. Next, for the parallel branches, we want to do 6. And for the conductors per slot, we do 10, 11, 9. So I will try to speed this up and we can do more fun stuff after. And so here we have the wire size. So you can select one size for all the wires, or if you are interested in do multiple wire size, you can do a mix and then just add your desired wire size here. You can do a diameter and give it a number. You can do multiple of them. But in this case, I'm just going to do a, okay. user define. I'll just pick one. I guess just 1.63. Okay, apply. Now, if we go back to the stator, we can see there's a stator already created. And next, so in this case, we can also we can insert a vent for our. Oh, so one thing I missed is we can also do a end installation for our windings. So let's do. So we also have the end extension here. So that's the extended length of the one side. Let's give a parameter. Speed this up. Slot linear 0.4. Wedge thickness. And let's go ahead to 0.5 for the layer insulation. So if you want some clear picture of how this thing looks like, what this means, I will give you a picture here. So basically we have all this wedge, linear, coil, curve wrap, and insulation, layer insulation here. So in case if you don't know what that means, or it's not in your mind, so we have, this is in the help. And if we go next, let's go ahead and define the vent. So double click on vent, we have the vent dots, width, and the pitch. We will set all this 0. Okay, and do the same thing. Do the same thing for the rotor. So we have this 5.7, 160. So 0.95 length. This is the same as the stator. We will give you a material. Okay, we have the stacking factors. It's cool. Next, we want to set a pole. So in this picture, you can see for each pole, it has different properties. So we have the height, all these types, and we can enter the values here. So we'll set all of this. 110. 5. No. Okay, we will give you a steel type. So let's put that 6. Okay. And next we have the insulation. And after we set up the rotor, we can also insert the damper for these rotors. But first we are going to set up the windings. Okay, so for the winding tab, we have 3 types here. So we are going to use cylinder in this case. 1, 380, 0.15. So let's put a name here. Number of strands, conductor, number of pole. So have the diameter here. Okay. So let's go ahead do this. So we'll give a thickness for the width and the width for the wires. 5. And we'll give those here. This doesn't really matter. SEO clearance. We have the with the cross height 4, 6. Okay. So next we are going to set up our dampers. Let me 10 per slots per pole, and we can define the slots type and give it a material. So maybe at the beginning, as we may know, the setup is always the most tedious part and it takes the longest time, but usually after we set up our design properly, the simulation usually takes very fast in this case. So let's get it a conductor. And one thing important to mention is we want to make sure all our parameter in this case is accurate, or else it will give you a very unusual error. So, and it takes a lot of time to figure out where the error comes from. So make sure we have our properties set up properly. So we have the pose. Okay. So now let's go back and see. We set up our motor in the already. So we have our stators and our rotors. So this is one pole of the rotors. If you want to see more, here's how the rotors looks like. So basically the motor setup is done, and next we are just going to do a solution setup. So I will go ahead and okay. So next analysis setup. I want to do a motor. What's the output power? I will just give you a number and rated voltage. Okay, so I will set a higher output power. The voltage will be 400, and we have the reference speed is 1K RMP. Operating temperature is 115. And next we are going to set up our power factors. 8 running connection. What's the exciter efficiency? We'll just give it 80%. So now our setup is done. Let's do a validation check. It looks no problem for everything. Then we are going to save this on the desktop. MAXWELL, experts, projects. I'll just give it a project 6. It's cool. So let's run the simulation. Okay, the simulation literally just takes seconds to finish. And next we want to see some results. And we can go to setup, just right click, and we can choose performance. That's it. Okay, let's do this. Local machine, blah, blah, blah. Okay. The simulation start, right? Analyze all. Okay. Simulation completed. Performance. This is strange. Where's the performance window? Okay, this might be a little bit of problem. Let me. Oh. Okay, no problem. It looks like crashed. So we always have a backup solution here. Let's go to our webinar. In experts, projects, and we have this one here. Okay. So luckily I saved the setup, so we don't have to do all the setup again. And let's do another analyze. Okay, let's do it again. Okay, now we have the performance. Here you can see all the different information data. So you can see your FEA input data, material consumptions. So you can see the flux or density, material density at for different material, and we can see the no-load operation. So this is used to see your flux density at your different part of your motors. So stator tip, flux density, yoke, so all these informations here. So if you need the data, you can check out the data here, and we can also export the data. We all have many other data. And next we have the design sheet. Here is the gives you the power and power factor and all the information setup is all shows in here. And next we can check out the curves. So here you can see your phase voltage, you can see your power factor versus torque, you can also see the torque versus speed, talking torque into tooth, etc. So you can basically see all your very initial, very basic result of the simulation at the initial step and check if this meets your requirement. If not, you can always go back and change your design to make sure it meets your requirement. And once it meets your requirement, next we want to bring this into our MAXWELL. So by right-click on Setup, we are going to create a MAXWELL design. So the good thing about RMSBIRD is it automatically generates a MAXWELL design based on all the information you give, and it will include all the boundary and excitation, all the stuff. So once you import it into MAXWELL, you don't usually need to do further setup in MAXWELL. You can just go ahead and do a very quick validation check, and then next just analyze it, and it will give you a result right away. Or maybe not right away, but takes a few more minutes. Seems so. But the good thing is you don't have to do all the setup again, so save a lot of effort. So if we go back, but in case you want to change any of your setup in MAXWELL and you don't want to go back and forth in RMSBIRD, you can always do it here in the material windows. So if let's say we go to the stators, we just double click on user defined parts. Here you can change all your properties and make a change in this case. And the boundary is already set for you, and we already have the excitation as well. So it also gives you a mesh, defined mesh. So you can also always change the defined mesh for accuracy, but the higher dense of the mesh will cause a longer simulation time. Now we have a changing simulation setup in this case. Then we just go ahead and do validation check, and looks like no error showing. And we just go ahead and analyze. So since this might take a few minutes, I will bring out a finished design so we can go ahead and see the results. So there we go. So this is the same one. And I believe okay, this is this one. Okay, so there we go. So basically, after you analyze it, you so the plot is already generated, but in case of you didn't see the result here, you can right click on the result and create transient plot or create field plot. So rectangular plot, and we will be able to plot any data of your preference. So here we have the torque versus time, and we have the current, induced voltage, etc. And if you are interested in doing other type of simulation, let's say it's eddy current or magneto simulation, you can go ahead and on the MAXWELL 2D tab, you just select the solution type. Here you can change your solution type. But be careful, if you change your solution type here, it may change some of your setups. So it looks like your analysis setup is gone. Some of the boundary setup is still here. The excitation is gone. All this type of stuff. So, but you can add a solution setup here. And you can also do a setup, number of paths, convergence, solver, and etc. So after you run a simulation, let's see, I have one design existed here. Okay. So basically the same thing after you set up your analysis. So here, you can just go ahead and validate your model. And once the validation is passed, you can go ahead and analyze your model. And this typically takes 10 to 15 minutes to complete the simulation. Okay, so looks like, oh, there's something I missed. Okay, let it finish. Okay, let's go back to this one. Validate it. Okay. So this is the magnetostatic simulation. So once we do the validation, it looks like our design is ready to run. So let's just do the analyze all, and it will run the simulation, and you can go ahead and plot different results. Okay. So next, I'm going to show you another feature. So in MAXWELL, we can always import a different CAD design to the MAXWELL. So here you can see we support set file, AutoCAD files, AutoDAX file, etc. And now if I'm going to import a new design here. Okay, maybe I need to create a new environment for this. Insert 2D. So here, this is a 2D simulation. Go ahead and import motors. Okay. Okay, so this is a permanent magnet motor. So we can see that all the material is not assigned, and we can just go ahead and give it some materials. And I have one is done here to save our. So here we have different number of poles for different magnets, north, and we also have the south poles. And if we double click if we go ahead and see the material, okay, we can see that this is this is a self-defined material, so it doesn't give you the origin here. So typically, if it's a material that existed in the library, it will give you like what kind of metal it is, or is it a permanent magnet, etc. But here, this is a self-defined material. And if we go next, we can see there's a router, there's a stator, and we also give it some inner band, outer band for the boundaries here. So bands, and we give it a boundary of vector potentials. So we give it a 0 Weber per meters at the outer range. So here, after we do an analysis setup here. So this is a transient simulation. We give it a 40-second simulation, and this takes 10 to 15 minutes. And we can go ahead and plot the torque. So this is our torque. Usually just right click here. And we can plot our torque. New plot. Maybe let's see. Oh, this one. There we go. So this is our torque based on time. But then we can also plot the field on our go ahead, plot the mesh field on our entire design by right-click field overlay, and right-click. We have the plot mesh. So this allows you to see the mesh. But if this is for the transient analysis. But if we go back to our magnetostatic analysis here, we are going to do a torque versus the phase. So here we can see there's a simulation of torque versus phase, and we can plot our flux line on our design. So basically just select the entire design here, and then just right click, plot fields. This is a flux line, and just click done, and this will generate the flux line, as you can see. And if you are interested in to see a rectangular plot, you can also plot the field here for the, let's see, design area. Yeah. Okay. So if we go next, if we want to add a skill to our design, basically we just need to go to the modeler. So MAXWELL 2D, we will have the design setting. So this is the 2D design setting, and we have go to the model setting. Here we can give you a model depth. So the depth is 0.4 meters. We can give some skew angles. So we set it as 15 degrees for the skews. And next, we just click OK. So this is already finished. The simulation is already finished in this design. Then we can just go ahead and plot our torque in this case. So do the same thing, and we have our torque with skew. So in order to compare the difference between with skew and without skew, we can drag the simulation result from the skew from without skew to skew, and we can see the comparison here together in the plot windows. Okay, so going next, and this is going next after we do all this simple simple analysis and plotting the results, we want to show you something cool. So we can, since this is a 2D design, and we already defined some, and as you can see in the design in here, we show you the depth of the design setting. We have the model depth. So we can go ahead and generate the 3D model based on this. And what we need to do is just go to design. Let's see. MAXWELL 2D, and we just need to go ahead and create 3D design. And we can give it a lens. We will give it a 200mm lens, and you will generate the 3D design automatically. Now we have the 3D design, and in this case we don't have to change any setting because all the setup is already done in MAXWELL 2D, so it will just bring over to 3D design. And you can see we have the 3D design here. For all the materials the same, but we will still need to do the boundary setup, etc. All type of stuff. So all the setup in this case will be similar to 2D design. We'll just give it a boundary and give it a decoration seal. We'll just give it a fill. We'll give it some analysis setup, add solution setup, etc. And you can also do the same thing. All the environment is the same as 2D. So there's no trouble in converging your 2D design and to 3D design, and you don't have to learn about the new thing in order to run the simulation properly. Okay, so this is pretty much all for today's presentation. So let me see if you have any questions. So looks like there is nobody having any questions. So I will post a link to the link of the introduction to MAXWELL and Esper later under the YouTube channel, and I will also give my contact information down there. If you have any further questions, feel free to contact me, and I'm happy to answer any question. Thank you.